Hi guys, BuildZoid here, and today we're going to be taking a look at my latest acquisition, the ASUS ROG Mars card, which is really two GTX 760s glued together. So that right there is a JK104 with which is configured to be a GTX 760, and this is the last of the Mars cards that ASUS has made. I don't think they're ever going to make another one, just because NVIDIA doesn't really do dual core cards anymore, and really ASUS did a Mars which was two GTX 285s together. They did a GTX 590 Mars, and then they did this one because NVIDIA didn't let them do one for the GTX 690, so there wasn't a 690, there wasn't a good version of a better version of the 690. Though, funnily enough, this thing right here has a better VRM than what you find on on the reference GTX 590 from NVIDIA, which is just like, yeah, that's awful, isn't it? There's a reason why that card is completely locked down from overclocking. So, yeah. But this is the ASUS Mars, and I obviously picked it up because it's a dual core graphics card, and I love these things. It's just like, they're so ridiculous, they're so impractical, they're so they're super complicated, because it's not like you don't just need to power two GPU cores, you also need to add the PLX chip, and then it's just like, oh, and you can't just make the PCB twice as large as if it was a single card. So you end up with some rather interesting, I think they're really, really interesting cards from a sort of engineering perspective. From a practical perspective, these things are completely freaking stupid. They're slower than if you bought two of the same card. And, SLI barely ever multi-GPU barely ever works properly. And they're just kind of impractical in every way, shape, and form. So there's really no good reason to get one of these. And these days, it's gotten worse, because the PLX chips that these use for their getting the PCIe slot to take two GPU cores, these don't work for some. These have problems with working on a lot of modern motherboards. Which is really, really annoying. So, for example, I've tested Z370, Z270, X470, and X299. And if on any of those, you actually plug the GPU into a PCIe slot that belongs to the CPU, it doesn't post. It doesn't work. The card basically doesn't get detected. I have no idea why. But that's just a thing. Now, if you put it onto the PCH, so on X299, I tried that, you put it onto the PCH and bam, it runs. But that's really less than ideal, isn't it? And it also means that on modern platforms, you can't actually run 4-way SLI with these. Which I'm rather annoyed about, because I was like, oh, if I get the chance, I'm totally picking up another one of these, and then we're doing 4-way. But it can't do that. It doesn't bloody work. So that's kind of unfortunate. But these do still work perfectly well on X99. So, and I do have a 6950X. So I might just do it sort of like retro benching or something. I don't know. It's not going to be really retro. It's just going to be like, oh, we get to test moderately old, very slightly irrelevant junk, with some really irrelevant junk. So anyway, so that's kind of why I picked it up. I just love these dual core GPUs, because they're so ridiculous. And let's get right into it. So this thing has more than twice as many VRMs that you would, as a regular GTX 760. So of course you have a V core, and this one right here, of course, powers the core over there. And then you have another V core, which is down here and powers the other core over there. So that's another V-core VRM. And then in between the two, you have a PLX VRM, because the PLX chip, yeah, it needs its own it needs its own voltage. So that gets powered by that. Then, because this card uses International Rectifier 3550s, we need a 5-volt power source. We need a 5-volt rail as well. So there's a little buck converter down here, which generates 5 volts. for the VR. Basically, it powers the VRMs on here, as well as some other things. Then we have memory power for both cores again. So we have one VMem here, and we have another VMem up here. And at this point, we've covered all of the ones that actually are big enough to warrant a buck converter, but not actually covered everything, because there's a whole bunch of low dropout regulators scattered around the board. You have one here, you have another one down here, another one over here, and if we go to the back of the board, we also have one over here. And yeah, there's just, yeah, absolutely plastered in voltage regulators. And in fact, this chip up here, I've not actually bothered to check, but the part number sounds like a series of LDOs that I've seen on other cards. So there's a good chance that's another LDO over there. The issue with that is I don't actually, like, again, I don't keep track of NVIDIA cards that well. And I know that NVIDIA cards, the 700 series, they have a PEX rail, so or a PLL rail, depends on which you prefer to call it. And I think it sits around 1.05 volts stock. And yeah, it's very low power, and it powered some of the PLLs and I think some part of the PCIe interface of the GPU core. But the thing is, there's like 2 LDOs for each core, so I'm not sure what the second one's for. Though it could be that maybe this is gate drive. But then, like, why is there actually, no, it isn't gate drive. I've checked that. This is directly wired to the power, the VCC pin of the power stages. So yeah, that's definitely not gate drive, because initially that was what I thought. It's got to be gate drive, right? Because what the hell else would that do? But no, I have no idea why there's 2 LDOs per core, because I don't know what the second voltage these cores are supposed to need, like the other voltage these cores would need is. And it's not for the GDDR5. It's not like GDDR5X. It doesn't need a VPP rail. So yeah, lots and lots of voltage regulators on here. Basically, if for some reason, if you wanted to e-power this thing, you could run into a really bad day where it's just like you need to, like, there's so many voltages that need to be present on this thing. The GTX 590 is actually the same story. There's just a crap ton of voltage regulators on those. So now that we've got all of the different ones out of the way, let's take a look at some of these in more detail. The V-Core VRM well, they're identical. They're the same thing twice. Let's start with the V-Core VRMs. This is a 1, 2, 3, 4, 5 phase, and it's real because you can't double into a 5 phase. It's literally not possible. It's an odd number. That's nice about, like, odd phase counts, is, like, they can't be fake. Because, well, unless a company says that they have an 11-phase VRM. And then they're lying because it's not an 11-phase. It has to be a something plus something else. So, yeah, but basically any odd phase count up to 7, true. It has to be true because you can't double into the odd ones. Because if you could, then they'd be even. That's like the whole definition of it. Anyway, the chip controlling these is an ASP1212, which is great because it's one of the few Digi Plus voltage controllers that are actually, like, have a public document that gives some information about them. It's not a full data sheet, but it is a product brief, so you get, like, the pinout and you get some of the feature list, which is plenty if you just want to do some volt modding and power modding and, those kinds of things. And it goes up to 8-phase output, and it's, of course, made by International Rectifier, which is now owned by Infineon. Here it is running in 5-phase mode. The actual power stages are International Rectifier IR35 50s, not 55s. Because I do believe the 3555 was not yet available at the time that this card was being produced. I don't remember. I didn't pay that much attention to part numbers at the time. Well, I didn't track them as intensely as I do now. That's for sure. So these are 3550s, and the difference between 3550s and 3555s is that 3555s are more efficient across a larger switching frequency range. These get really, really inefficient past 500 kilohertz, and the 3555 is, like, I think starts to have that same kind of issue with efficiency past sort of the 600 or 700 kilohertz range. So that's why the 3555 exists. It's an upgrade over the 3550. But nonetheless, this is still a really, really powerful power stage, and it was used on top-end motherboards for a long time. So, as well as top-end GPUs, because there really wasn't anything much more powerful than your 35, 50, 60 amp power stages at the time. And so you do have 5 of them, and that means this VRM has a theoretical maximum output of 300 amps. Now, it's obviously not going to hit that, because if you actually tried to push 300 amps through it, it's going to get more than a little bit warm. And we're going to get to that once we go through the heat output figures for the VRM. So then, GTX 760 now again, don't follow NVIDIA that much, so I kind of rushed some research on how much power a GTX 760 would use while getting overclocked, and these are the figures I came up with. I'm not 100% certain that they're accurate, but they seem to be relatively close. So 1.2 volts, 120 amps. This would be around 1200 for around 1250 megahertz. Let's just put a M on there. So 1.2 volts, 120 amps, and there you'd be looking at about 11 watts of heat output, which is really, that's actually really, really cool. That's really, really efficient, which makes sense because you're nowhere near the maximum output of the 60 amp power stages. In fact, this is right around, I think, the efficiency sweet spot for them. Next, 1350 megahertz, and again, I have no experience with NVIDIA. I think this voltage is too high for that frequency, but I'm not sure, so I'll just stick with the frequency being too low, because ultimately, raising the frequency wouldn't change the power, the current draw figure that much. Though it would make it higher, because obviously the more times you switch the transistors, the more power they use. So, 1.35 volts, 145 amps, and you'd be looking at around 15 watts of heat output, which is, again, really not that bad. Then, I'd assume around 1500 megahertz. 1.5, well, actually, no, that's a bit high, so 1450 megahertz. 1.5 volts, 170 amps. You'd be looking at about 20 watts of heat, which, again, not really that bad. And then there's liquid nitrogen. Then there's the issue of liquid nitrogen, because liquid nitrogen makes the 700 series, clock really high. There's a 760 on the HW bot ranking doing 2 gigahertz. And I'd be lying if I said I didn't want to get 2 gigahertz also, and ideally on both cores. So, I tried to, get some reading up, get some data on, Kepler overclocking on LN2. Unfortunately, there's not that much detail available there, as far as the power consumption is concerned. Plenty of information on what how to, break world records on a 780 and 780 Ti, assuming you have one of the LN2 focused special editions, so a Matrix or a Kingpin or a Lightning, but not much detail on what happened, what kind of power draw figures those cards push, and what kind of scale, what kind of power draw scaling you get. So I don't actually know how much load the VRM would have to sustain. But the calculator seems to be pretty intent that at around 2 gigahertz, 1850 megahertz, 1.65 volts, the calculator says it should hit close to around 250 amps. Now, I think it should actually be way lower due to the fact that the GPU core is going to be really, really cold, and so your leakage is going to be way down there, but the calculator doesn't know how to compensate for that, and I'm not just going to, make stuff up to make it sound less ridiculous, and ultimately, it'll be nice to know what'll definitely be too much. So 250 amps, you'd be looking at about 45 watts of heat, which still isn't a catastrophe. Now, this starts being concerning, okay? That is actually really concerning considering how small these VRMs are, but you could get away with it for shorter benchmarks. Also, the PCB would hopefully be frozen through depending on how cold you're running the GPU. And, you'd have a 2000 RPM or higher RPM fan pointed directly in between the LN2 pots to keep the VRM cool. So that should, I think that be survivable for the shorter benchmarks. Maybe not Unigine Heaven, but then I don't think Unigine Heaven would get that hot. because it's not quite as heavy. Like, the heaviest benchmark out there is 3D Mark 11. And 3D Mark 11, well, might be a problem. 3D Mark 11 might be a problem because it gets really hot on some of its tests. Now then, 2 gigahertz, 1.75 volts. Calculator says at that point it's going to hit almost 300 amps, and I'm just going to go with 300 amps because it makes the math easier for me when looking at the data sheet. And at that point, you're going to be looking at around 74 watts of heat output. No, that is not going to work on these. That, it's going to need a heatsink at that point. Like, there's no way it's not going to, and like a heatsink with actual fins and some mass and, you know, some actual cooling capability. Unfortunately, what the card comes with stock is basically a flat aluminum plate that goes under the heatsinks. So there's not much in the way of cooling on this thing to start with, which is kind of annoying, actually. And it's not like I can just bodge a VRM onto here. Bodge a heat, like, it's not particularly easy to, like, get heat sinks onto here, so, because I really don't want to glue them on or, like, tape them on. So, yeah, it'll be interesting. I guess I'll just stick a temperature probe in the VRM, and if I start seeing it run, start noticing it running away, then shut down the benchmark before the VRM goes up in smoke. That's assuming it even scales to that voltage, or I don't break the card with condensation before I get there. So, you know, who knows? Like, doesn't, like, just because theoretically it can doesn't mean it really will. But, you know, best to be prepared. And I think, honestly, at that voltage and that frequency, yeah, it'll probably be pretty ridiculous. But nonetheless, for your sort of day-to-day overclocking, and even like 1.5 volts is not day-to-day overclocking, that's going to kill a chip if you run it for long enough at, you know, ambient temperatures. But for this section, like, this VRM does actually really, really well. Which is unsurprising because, you know, 60 amp power stages, they're good. It's kind of why they exist. Then for the extreme overclocking stuff, I think, like, it should still be able to do at least 1800, 1700 megahertz. I'm pretty sure I could probably push that on the card, assuming I don't run into other issues, because that's the other thing. You always get other issues. Now then, let's move on to the rest of the board. Now, the, let's see, which one's more convenient? This one looks better, even though you still can't read it. So the memory VRM is a single phase, and it uses this chip right here, which is a dual NFET from Texas Instruments. It's the TI CSD 87350. This is a 40 amp dual NFET. This is the same, like, if you have a Maximus 9 Apex motherboard, these are the MOSFETs used for each of the phases for vCore. So, and for memory power, this is massive overkill. This is just completely ridiculous overkill. GDDR5 does not pull that much power, that much current. So this is massive overkill. I would have preferred two-phase memory power just because memory does seem to generally, like, benefit from having more than one phase, but hey, you know, it's like this thing's already really, really cramped. Though, interestingly enough, I do think NVIDIA managed to cram a dual two-phase memory power onto the GTX 590. Admittedly, each of those phases was anemic as hell, but there was two of them. So, you know, it is doable. It's just not, like, it gets even more ridiculous than trying to cram everything that is on here. So, yeah, you know, memory power, plenty powerful enough. And the memory VRM is controlled by this chip right here and this chip right here. And these are from Excelliance Moss Corporation, who also make all of the, this LDO right here, same company making that. But these are EM5305s. And there are single-phase buck converters, very, very easy to modify. They do have a public data sheet. You stick that into Google, and if your Google has my filter bubble on it, it'll find the data sheet for these. So that's nice. Now then, what if we wanted to lift the power limit? Because if we look at the front of the card again, we have a shunt here, we have a shunt there, we have another shunt here, and I do believe a shunt there. So, you could put liquid metal over those. You could try solder over those, though I'll tell you this. If you solder over, like, if you literally just build a solder bridge over a shunt, generally what you'll find is that the NVIDIA driver gets really, really triggered about the power consumption being reported way too damn low, and it won't let you run any benchmarks. And believe it or not, the GTX 590 actually does that. That's how I found out that, like, I thought it only affected the 10 series cards, but no, I ran into that same issue with the GTX 590, which is why I'm throwing out the warning here. And I'll actually demonstrate what it looks like eventually. I unpacked the GTX 590, I tested that works, and then something happened, and I never got around to producing the video. So that's sort of on the stuff to do, the great big long stuff to do list. Anyway, all of those shunts are being monitored by a couple of chips around the board. One of them is here, another one's down here, another one's down here, and another one is here. And I've not actually checked which way they're wired, so I'm not going to tell you how to do the mod, but these are all Texas Instruments INA 219s. And these are basically the 3221's little brother. Well, that's not really right. It's like if you took a 3221 and cut it into 3 pieces. Because these are, the 3221 can monitor 3 different shunt resistors. The INA 219 can only monitor 1 shunt resistor. And there's 4 of them on this board to monitor the 4 shunts on the front of the card. So if you want to modify the power limit by basically like just faking the existence of a shunt, what you would do is you would set up a 12 volts to ground voltage divider, and you'd set it up so that you have like 12 volts and then minus 12 volts, and then you'd have, I think one I did was like 120 kilo ohms to 30 ohms, something like that, because basically what you're trying to do is you're going to have 12 volts, and then you're going to have a resistor, right? And then you're going to have another resistor, and then you're going to have ground. And what you want is this point right here to be about like 11.997 or something like that. It depends on what you're dealing with on your GPU. On this one, actually, if you wanted to fake, because this one, if we look on the front of the board, we can see that those are, like, that's a little 2 on there. Those are 2 milliohm shunts. So you can't, like, if you want to fake 1 amp, if you want to fake 1 amp of current draw, so 12 watts of power consumption on every single one of these, what you're going to want to do is you're going to want to actually drop from 12 volts to 11.998 volts. And once you get that amount of drop, what you would do is that you would then pull it to the input pins of, well, you'd do something like that, and you would do it to every single one of these on the board. So that would be a mess of wires, but it would completely remove the power limit, because for the rest of its life, the card would think that it's pulling 48 watts all the time. And if you wanted to, you could even go with a lower voltage drop of like 999 volts, so 1 millivolt, which, again, you just need to fine-tune your resistor values to get the drop you want, and you'd have even less power. Like, the power consumption reported in the software would be even lower. So that would eliminate any, though I do believe you can BIOS mod 700 series NVIDIA cards, but I'm probably going to do this just because this is in my, like, for me, this is easier than trying to figure out how to BIOS mod NVIDIA cards. I'm not that interested in learning it, and there's other modifications that I have to do on this card anyway, and at that point, you know, it's just like, well, do everything. So, yeah. But that is the 760 Mars, a rather interesting PCB because there's 2 GPU cores on it. It has pretty solid VRMs, especially considering how cramped it is. These are actually really solid. And yeah, and it fits LN2 pots, which is why I'm so excited about it, because it's like, yes, I can run this on LN2. Unlike the GTX 590, because the GTX 590, that thing doesn't have, like, the mounting holes on the GTX 590, they're not even rectangular. Like they don't like if you like these are square, right? Which is like normal for most mounting holes, and the GTX 590 ones are just kind of all over the place, and it's just infuriating because nothing fits on it because of that. So yeah, but this will fit an LN2 pot. The VRMs seem like they should be fine, even up to LN2, levels of overclocking. And all of the chips around the board have enough information about them that you can mod them. And the memory power is good enough. The VCore is good enough. Yeah, I'm happy. It sucks that this, like, from a practical perspective, from like gaming performance perspective, from benchmark performance perspective, this thing sucks. But it's just kind of, it's cool and unique, and that's why I wanted it. So, yeah. That's it for the video. Thanks for watching. Like, share, subscribe, leave a comment, questions, or suggestions down in the comment section below. And if you'd like to support what I do here with actually hardcore overclocking, I have a Patreon, a PayPal. There's also t-shirts you can buy down in the description below. And I think I'm going to head off to do some more AM4 motherboard testing because I've not actually done any this week. It was mostly X299 and then cleaning up the place because the place has gotten to a mess, like terrible mess. Oh, and spent a lot of time cleaning this thing because it was secondhand. So, yeah, that's it for the video. Thanks for watching, and goodbye.